In this video, we're going to discuss triple integrals. We've done double integrals, and now we're going to have triple integrals. Triple integrals can represent the volume of a solid region Q. We'll talk about how to set that up. We'll talk about using a triple integral to find the mass of a solid occupying the region Q given its density function. And we'll talk about changing the order of integration with a triple integral. Since we understand double integrals, going to triple integrals isn't that difficult. Let's say that we were trying to find the area between y equals f of x and y equals g of x, and between two vertical lines, x equals a and x equals b. Well, we found a single integral that represented the area between these two curves. But we could also find a double integral that represents the area between those two curves. We said, we'll just take that interval from a to b and subdivide it into n subintervals of equal width. So we've got n subintervals in the x direction. And you've got this, 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 and this. And let's also make m subintervals in the y direction. Now, with this, rather than finding the area between the two curves using rectangles with a height f of x sub I minus g of x sub I, and then subtracting, instead of doing that, we're going to find the area between two curves by finding the area of each of these little blocks and then adding them up. Well, the area of one of those little pieces, the area of the ijth rectangle, is just delta x times delta y. So the total area is equal to the limit as the number of rectangles in the x direction and y direction go to infinity of the double sum as I goes from 1 to n and as j goes from 1 to m of delta x times delta y. Now this is exactly right, provided that this is a rectangle. If it's not a rectangle, this principle applies, but there are going to be some rectangles where we don't actually get any area, so we have to be careful about that. But this will eventually lead to a double integral. And because y goes from a function to a function, we would integrate with respect to y first and then x. And we'd say y goes from g of x to f of x, from the bottom function to the top function, and x goes from a to b. So that's one way that we can represent this area. Now, thinking about finding volume using a triple integral is very similar. Now, I would never find the volume of a rectangular box this way, but we could create n subintervals in the x direction, m subintervals in the y direction, and let's say L subintervals in the z direction. And so we get this. So you've got n subintervals in the x direction and m subintervals in the y direction. And z subintervals, or excuse me, L subintervals in the z direction Let's say you're trying to find the volume of a rectangular box. Then it might look something like that. It's a horrible box, sorry. Yeah, he didn't do a very good job making those lines meet up. But I think you get the idea. Basically, I'm taking my rectangular box and I'm splitting it into a bunch of little cubes. I didn't do a very good job with my lines though. So you go to this and you find one of these little cubes. Maybe there's a cube sitting right here. This is x, that's y, and that's z. And if I want to find the volume of this whole thing, well, I can just add up the volumes of all the little cubes. Well, one little cube has these dimensions. That's delta z. This length is in the x direction, so that's delta x. And this is delta y. So delta v might be represented by delta x times delta y times delta z. So the total volume is the triple sum. I want all the subdivisions in the x direction, so I want I to go from 1 to n. So that would give me go from the back to the front. And then I want j to go from 1 to m, so that would go from, so that's I going from 1 to n, j going from 1 to m, would take this little row and then extend it this way. And then I want k to go from 1 to l, and that would take that layer and then move it all the way up. And so I'd add up all of those pieces and I would get the total volume. And if this isn't a rectangular box, maybe I need to take the limit as the number of subdivisions in all three directions goes to infinity. And that works if delta x, delta y, and delta z are all the same. Not the same size as each other, but all the subdivisions in the x direction are the same width, delta x, and all the subdivisions in the y direction are the same width, delta y, and those in the z are all the same width, delta z. So it's not delta z sub I, so it's not a different delta z from piece to piece. If you do that, then what you get is a triple integral. So total volume is the triple integral of this, which will become a dv in the limit. And if we're talking about a solid region Q, that's the triple integral over Q. Now, if we're talking about a rectangular box like this, obviously x goes from a constant to a constant, y goes from a constant to a constant, and z goes from a constant to a constant. But most of the time, that's not what we have. If we want to find the volume of a solid region Q, I'm still thinking in terms of volume between two surfaces, as we studied earlier. So maybe Q looks like this. Maybe this bottom function is z equals f sub 1 of xy, and this top function is z equals f sub 2 of xy. So z is going from this function to this function. In practice, when I'm evaluating this double integral or triple integral over Q to find volume, usually this is what it looks like. Z is going from a bottom function to a top function. So it's a smaller value of z to the larger value of z. And I'm going to take a shortcut. This goes with dA, and dA can be dx dy or dy dx, but we're finding that, we're describing that region R, and that region R is the projection of our solid region Q onto the xy plane. Oh, this is Q, sorry. The interior of that is Q, and this is not Q, this is R. So the projection of Q onto the xy plane. And often the way we find that projection is we find that boundary. And that boundary often requires setting this z value equal to that z value. And then you can describe this region R any way you want. You can let x go from a function to a function and y go from a constant to a constant, or the other way around. So triple integrals represent volume now. This dx, dy, dz can be thought of as a dv, just like dA was dx, dy, or dy, dx. So let's look at some examples. Let's say someone asks you to sketch the surface given by this. Got a triple integral representing the volume of a solid region. We've got the integral from -1 to 1 of the integral from y squared to 1 of the integral from 0 to 1 minus x. We're integrating with respect to z, and then x, and then y. And this represents the volume of some solid. So the first thing we're asked to do is sketch the solid whose volume is represented by the triple integral. And we're also asked to change the order of integration. We didn't discuss that, but I think it makes a lot of sense. When we were talking about area, we could integrate with respect to y first and then x, or integrate with respect to x first and then y. With triple integrals, the same thing is true. We can integrate with respect to any one of these variables and then the other two. So you actually have 6 possible orders of integration. Now generally I tend to stick to this. I like to let z go from a bottom function to a top function and then look at the projection onto the xy plane. Since I still think this way, this is usually the way I go if I want to represent some solid region Q in 3-dimensional space. But theoretically, we could let x go from a function to a function. So it would go from a back function to a front function. So we were going from smaller values of x to larger values of x, and larger values of x are closer to us because of the way our coordinate system is oriented. So we could let x go from a function to a function, and y go from, and then project onto the yz plane. We could let y go from a left function to a right function and then project onto the xz plane to find the bounds for the other two variables. But generally I still think like this, so I tend to stick to this if possible. But it's good for us to try thinking about this, thinking about representing this volume in different ways. So we'll practice changing the order of integration. And sometimes that's actually necessary to evaluate the integral. Not integrals for volume, but integrals of other functions. So let's sketch this solid whose volume is represented by the triple integral. We'll do the best we can. It's difficult to draw. And then we'll think about changing the order of integration. And we are asked to change it to a particular order. We're asked to change it to dx, dz, dy. Okay. First we'll sketch the solid. In order to do that, we use the bounds for each variable just to describe some surfaces, because our solid is bounded by all of these different surfaces. These innermost bounds go with the variable z, so this is telling us that z starts at 0 and goes to 1 minus x. And this one right here tells us that x starts at y squared and goes to 1. And this one's telling us that y is between -1 and 1. Okay. So probably the easiest way to start this is to not sketch this z equals, or these bounds for z first, but instead to sketch the region in the xy plane. So this is telling us z goes from this bottom function to this top function. This is a description of the region R, the projection of our solid onto the xy plane. So let's look at that. Now this represents 4 different equations. I've got x equals y squared, x equals 1, y equals -1, and y equals +1. So y equals 1 is here, y equals -1 is there. Just a couple of horizontal lines. X equals 1. Look like this. And x equals y squared is a parabola on its side, and it turns out to intersect right there at x equals 1, y equals -1, and x equals 1, y equals 1. So our region R in the xy plane looks like this. Notice that we have positive and negative values for y, and it's opening, we've got a parabola that's opening on the positive x-axis. So when we try to graph in 3-dimensional space now, you want to change your orientation just a little bit. We've got a parabola opening on the positive x-axis. So it looks like this. And then x equals 1 is right there. So this is the region R. Okay. Now, the solid is bounded below by this region R, but it's bounded above by z equals 0, which actually happens to be the region R. The z equals 0 is the xy plane. And then it goes to this other surface, z equals 1 minus x. Now z equals 1 minus x is a plane, but it's also a cylinder. And it's a cylinder because there's no y involved. So I can really think of this as the line z equals 1 minus x that you would see in the xz plane. And then remember that you're going to see that line over and over again infinitely many times because y can be anything. The easiest way to sketch this plane is to set z equal to 0 and solve for x, set x equal to 0 and solve for z. When x is 0, z is 1. And when z is 0, we have 0 equals 1 minus x, so x would have to be 1. So that's the part of the plane that we would see. And we're going to get this plane actually extends back behind the yz plane and it extends below the xy plane. But the part that we would see where x and y and z are all positive, or when x and z are positive and when z and y is negative, looks something like this. So we've got this plane. Looks roughly like that. Now our solid is bounded above by this plane, but it's bounded below by this portion of, like, it looks like a parabola, but then we've sliced it and then we've shaded this region right here. So you want to keep that in mind. The solid that we're looking for, I believe it's going to look something like this. So actually, let me change the orientation a little bit. I don't know if I can. It's really hard to imagine drawing this. What I'm seeing in my head is like a wedge, kind of looks like this shape from the side. I'm not good enough at drawing, sorry. But the bottom is a parabola and the top part is a flat edge. So basically I've got a parabola that looks like this, and I've got a plane intersecting that parabola. And that plane just gonna do the best I can, guys, sorry. So here's my plane. So I've got my parabola. It looks like this. And then I've got a plane that's meeting it on an edge like that. It's horrible. Sorry. Maybe I should have cut out a little tiny parabolic planar piece. If I have some time to redo videos this summer, I will. Okay. So, this is really bad. But you've got like a plane like going like this. Never mind. Okay, I'm trying to get you to visualize this. So you've got a parabola on the bottom, and then you've got a plane that's kind of coming up like this. And there's like this parabola shape over here. So, like, my hand is the plane. Sorry about my manicure. COVID-19, you know, I can't go get my nails done. But yeah. It's like something like that. And there's your plane. Okay? So you've got a plane. It goes like this. Crosses the x-axis, then it goes up. Roughly. Okay. So we were asked to sketch the solid. We did the best we could. Tried to create little models unsuccessfully. Looks like looks bad. Okay, so we were asked to sketch that solid, and we did. Now we're asked to change the order of integration to dx, dz, dy. Now remember how we were thinking about this. We were thinking of z as going from a bottom function to a top function. So going from the xy plane to this plane, z equals 1 minus x. And meanwhile, we found the projection of that solid onto the xy plane. We called that the region R. And that describing R was done out here with these outermost bounds. So this says z goes from this function to this function, and R can be described this way, where x goes from this function to this function, and y goes from that constant to that constant. Now we want to do this in a different order. We want to integrate with respect to x first, and then z. So now I need to think in terms of x going from a function to a function. Now, when I'm thinking of x going from a function to a function, sorry about the bad pictures over there, it didn't work out. I want the ones that are farthest away from us first, so the ones with the smaller x values, and then I want the larger x values up front. So it's going to go from back to front. If the z values were going from the bottom to the top, x is going from the back to the front, y is going from the left to the right. So the boundary for x is still given by this parabolic piece. This is x equals y squared. So it's a piece that looks like this. So it's actually going from x equals y squared, that's on that side, to the plane. So when I'm coming up with my bounds for x, so this is the function that's farther in the back. So this is from the back function to the front function. Just because of the way our coordinate system is oriented. And in the back, x is equal to y squared. In the front, we've got that plane. So I need to take this equation of the plane and I need to solve it for x in terms of z instead of z in terms of x. So I've got z equals 1 minus x, so z minus 1 equals negative x, and let's multiply both sides by negative 1. So x is equal to 1 minus z on that plane. So our back function to front function is from x equals y squared to x equals 1 minus z. Now this is where it gets tricky. We're asked to change the order of integration to dx, dz, dy. And that means I need to integrate with respect to z next, and then y. And this has to describe the projection of the solid region onto the YZ plane. Now this is a little tricky. We've never had to do that before. Let's think about what we did when we were projecting onto the XY plane. In order to find the projection of some surfaces like this onto the XY plane, usually what we did was we set the Z value on this surface equal to the Z value on that surface, and that gave us some boundary. And because of the picture, we knew that we were talking about the interior of that boundary. So this gave us the equation for the boundary of R, and we knew we were sketching inside because the volume was inside that region. So we have to do something similar here. I'm looking at this solid, and I'm imagining projecting it onto the YZ plane. So that's like the back wall right here. There's the YZ plane. And in order to do that in this order, like they want me to, I need Z to go from a function of Y to a function of Y, and Y to go from a constant to a constant. Well, I think we can see what the constants are going to be for Y, because the constant values for Y over here were negative 1 and 1. When I project onto the Y-axis from this solid region, the Y values are still going to go from negative 1 to 1. So that part is easy. The harder part is finding the boundaries for Z. Say, what does Z have to be as a function of Y? Well, here's what we're going to do. In order to figure out what Z is as a function of Y, I need to figure out where this parabola, x equals y squared, meets the plane 1 minus z. So I have to set this x value equal to this x value. Just like we did with the z's, we often set the z's equal to each other and then looked for that curve, that boundary. We're going to do the same thing here. We're going to set the x's equal to each other and then look for a boundary. So if I solve this for z as a function of y, I get that. Multiply both sides by negative 1, and we get that. So what we're looking for, or what we have here, is this. Here's z, here's y. The z equals 1 minus y squared. It looks like this. And y ranges from negative 1 to 1. So this is the projection onto the YZ plane. And I think that that makes sense. If you look at this picture, you imagine projecting onto the YZ plane. Doesn't it look like it's going to be z equals 1 minus y squared, that parabola facing down that shifted up 1 unit? I think it does. Okay, so z is going from a function of y to a function of y. Well, it's just going from z equals 0 to this function, which we just found was 1 minus y squared. All right. Excuse me. So we're asked to sketch the volume, or the solid whose volume is represented by the triple integral, change the order of integration, and we have. Now, if we've done everything correctly, the integral with these bounds and the triple integral with these bounds should give us the same answer. So let's check and make sure it works. The original integral was this. If I want the volume of the solid, That's what this is supposed to represent. I just integrate from the inside out. It's just like a double integral. You just do it 3 times instead of 2 times. And there's an implied 1 there. So we integrate 1 with respect to z, we get z, and evaluate from z equals 0 to z equals 1 minus x. And I substitute in 1 minus x, I get 1 minus x minus 0. And then we anti-differentiate this with respect to x. So we get x minus 1/2 x squared, just using the power rule, and evaluate from x equals y squared to x equals 1. When you substitute in x equals 1, you just get 1 minus 1/2. When you substitute in x equals y squared, you get y squared minus 1/2 of y squared squared, that's y to the 4th. All of that is multiplied by dy. And so we end up with 1/2. If we distribute that negative of negative y, or 1/2 minus y squared plus 1/2 y to the 4th. And we're integrating with respect to y. Antiderivative of a constant is that constant times y. Here, add 1 to the exponent, divide by the new exponent, bring the 1/2 down, then add 1 to the exponent, divide by the new exponent, plug in -1 and 1 and subtract, and we get 1/2 minus 1/3 plus 1/10 when x is 1. And then we're subtracting when when y is 1. When y equals -1, we get -1/2 plus 1/3 minus 1/10. And if we distribute that negative, we see we get a 1/2 there, and a minus 1/3 and a plus 1/10. That's the same thing we had over here. So that's our answer. And if you want, you can get a common denominator. Multiply this one by 15 over 15, multiply that one by 10 over 10, multiply this one by 3 over 3. And you get 18 minus 10 is 8. 8 times 2 is 16. We get 16 over 30. Divide by 2 and divide by 2. And you get 8 over 15. That's the volume of this solid region. Okay, using the original triple integral. If we've done everything correctly, where x is going from this back function to this front function, and we looked at the projection of the solid onto the yz plane, and we got this, and we described it this way. When I integrate using these bounds, I should get the same thing. Now, I should get that 8 over 15 again. Now let's write down the appropriate triple integral. Now this is the way it works. The innermost variable can depend on the other 2 variables. So x is going from a function of y and z to a function of y and z. So I need to integrate with respect to x first. They actually told us it was going to be dx, dz, dy. But these bounds for x can depend on z and y, and they do. Now the bounds for z aren't allowed to depend on x, because I've already integrated with respect to x. I've already replaced all of the x's with functions of y and z, so I can't bring x's back into the picture after I've integrated with respect to x. Z is allowed, or the bounds for z are only allowed to depend on the variables past it. So the bounds for z can depend on y only. And they do. Z goes from 0 to 1 minus y squared. And the bounds on the outside have to be constants in order for us to get a volume out of this. So let's evaluate this. Hopefully we get the same answer that we got the other way. Just going to use a little bit of this paper. And we're integrating with respect to x first. And this is what I've got. The antiderivative of 1 with respect to x is just x, and we evaluate from x equals y squared to x equals 1 minus z. According to the fundamental theorem, we get this evaluated at the upper bound minus this expression evaluated at the lower bound. Okay. Now we want to integrate with respect to z, treating y as a constant. So you're doing this innermost integral again. Antiderivative of 1 with respect to z is z. The antiderivative of z with respect to z is 1/2 z squared. It's just the power rule. And the antiderivative of this constant with respect to z is that constant times z. And then we evaluate from z equals 0 to z equals 1 minus y squared. And we'll evaluate that result from -1 to 1. At 1 minus y squared, we get z. That's 1 minus y squared minus the quantity, or minus 1/2 times the quantity, 1 minus y squared squared, minus y squared times z, which is 1 minus y squared. All of that times dy. And we should also evaluate, I don't know why it's so bright there. We should also evaluate this expression at z equals 0, but then we just get 0. So there's not much going on there. Now let's finish this. Now, in order to finish this, it helps if I just do a little bit of algebra. That's 1 minus y squared times 1 minus y squared. Over here, I'll distribute the negative y squared, so I've got negative y squared plus y to the 4th. And here, I should FOIL. First times first is 1, outer times outer is negative y squared, inner times inner is another negative y squared, last times last is y to the 4th. Distribute the negative 1/2. Negative 1/2 times negative 2 is positive 1. And the y squared and the negative y squared reduce. Okay. Any other like terms we can combine? 1 minus 1/2 is 1/2. So those are taken care of. Negative y squared, I'll just bring that down. And then I've got y to the 4th minus 1/2 y to the 4th, so that's 1/2 y to the 4th. Antiderivative of this with respect to y is that constant times y. Then we add 1 to the exponent, divide by the new exponent, bring the 1/2 down, add 1 to the exponent, and divide by the new exponent. Substitute in -1 and 1 and subtract, and look at what we get, guys. We have a 1/2 minus 1/3 plus 1/10 again, and then subtracting a negative of that, it ends up being 2 of those. And we still get that 8/15 that we got before. So those two triple integrals are two different ways of representing the same thing. Now, I would probably stick to this. If I have a choice, I'm going to let z go from a function of x and y to a function of x and y, and look at the projection on onto the xy plane, because that's what we're used to. But we could change our perspective. We could let x go from a back function to a front function and project onto the yz plane. We could also let y go from a left function to a right function and project onto the xz plane. So there are lots of possibilities. But normally I stick to that first one. Okay, so that first problem we looked at, we were given a triple integral and asked to sketch the solid whose volume was given by that triple integral and change the order of integration, and we did. Here's one that's a little bit more straightforward. Instead of giving you an integral and asking you to sketch the solid, we're asked to find the triple integral representing this volume of the solid. So we're trying to find the triple integral representing the volume of the solid region Q, bounded above by z equals 4 minus y squared, and below by z equals 3x squared plus y squared. This one's a little odd. That's okay. The first thing that I would do for this is sketch it. And it doesn't have to be a perfect sketch, it just has to be a good enough sketch for us to get a sense of what's going on. Okay, so first of all, z equals 4 minus y squared. There's no x in that, so that's a cylinder. So I can just think of that as that parabola, z equals 4 minus y squared in the yz plane. When y is 0, z is 4. And when z is 0, we get 4 minus y squared is 0, so y would have to be plus or minus 2. So we have this parabola facing down, and that's true for any x value. X is free to be anything. So what we would see is that same parabola over here. And even behind us, behind the x or the yz plane. Not doing a very good job with my picture. I hope you get the rough, it's a very rough picture. Oh, that's really bad. Very rough. Okay. Very, very rough. Okay, so that's vaguely this z equals 4 minus y squared. It's just another one of these. It's just a parabola, but x is free to be anything. So it kind of looks like a bread, what's it called? The bread container. Bread box? There we go. Looks like a bread box. It's just a little bit more parabolic in its shape. That's the upper boundary. And the lower boundary is this. See, what is that? Do you remember? X is squared, y is squared. Both of these are positive, and it's equal to z to the first. That's another elliptic paraboloid. So what we'll get here is an elliptic paraboloid facing up. So this is z equals 4 minus y squared. The elliptic paraboloid facing up would look like this. Now it's going to be a little longer in one direction than the other. I know it's counterintuitive, but that 3 multiplying the x squared actually makes it smaller in the x direction as compared to the y direction. So it's sort of skinny in the x direction and like wider in the y direction. And we've got this surface below this sort of bread box thing, and we want the solid in between them. Now, in order to figure out the projection of the solid region Q, which is formed by taking this and intersecting it with this and then projecting onto the xy plane, in order to find that region R, we have to set the z value on this sort of breadbox shape equal to the z value on this elliptic paraboloid. I wanted to draw this separately so that I could draw the region R over here, and that would give me a better sense of what my solid would look like as well. So we're sketching Q as best we can, not quite there yet. And the next thing I want to do is sketch R. And one way that I can sketch R is I can set the z's equal to each other. So I've got 4 minus y squared is equal to 3 x squared plus y squared. And I can graph this. So I will add y squared to both sides. So I have 4 equals 3x squared plus 2y squared. And that's an ellipse, so it's going to meet in an ellipse. In order to write the ellipse in standard form, I'll divide both sides by 4. So I end up with 1 equals 3x squared over 4 plus y squared over 2. Now, the way we typically like to write this is we like to write this as x squared over a constant a squared plus y squared over a constant b squared. So here's the trick. Instead of multiplying this x squared by 3/4, I'm going to divide it by the reciprocal. I'll divide it by 4/3. And that 2, I'll call that the square root of 2 squared. And this I really want to write as something squared. So I'll take the square root of that. So I'll have a 2 over root 3 there. I know that looks really bad, but this tells me how many units to go in the x direction from the center. It's 2 over square root of 3. So it's about 1.15, so we want to go 1.15 units in the x direction, adding and subtracting from that center point, and we want to go square root of 2 units in the y direction, and square root of 2 is, I believe, 1.4. Yeah, about 1.4. So again, I said it's a little longer in the y direction because of that 3, and it is. So here we are. Here's x equals 1. X equals 2. We want to go a little bit in the x direction to 1.15, and then we want to go back to 1.15. And then in the y direction, we want to go left and right 1.4 units. So maybe there and there. So that's our region R. If you're saying, what on earth? I know, me too. I've got an elliptic paraboloid. It's fitting under here somehow. And it's intersecting with this surface over that ellipse. I know it's very strange looking. But that is my very rough graph of the solid region Q. The interior of that is Q. So we want the solid interior region between z equals 3x squared plus y squared and z equals 4 minus y squared. Okay, so what were we asked again? We're asked to find the triple integral representing the volume of the solid region. And then, yeah, let's just find the triple integral. Actually, we've done most of the legwork. We've done most of what we need to do. So we sketched the region, we sketched Q, we sketched R, and that's really enough to get us our bounds. So Q goes from, or the z values, excuse me, go from the bottom function to the top function. And the bottom function in this case is the elliptic paraboloid. And I like to integrate with respect to z first, so we'll do that because I think it's the most intuitive for all of, or out of everything that we've learned. So this is our top, or our bottom function for z. And the top function is that cylinder. I'm sorry, my picture is so rough this time. Okay. And then the region R in the xy plane was given by this. It's really pretty bad. We're going out -2 square root of 3 units, or divided by square root of 3 units in the x direction, plus and minus, and then we're going out square root of 2 units in the y direction. Add and subtract square root of 2 units in the y direction. Ooh, that is an ugly looking ellipse. Not just because it's not a pretty graph, but I don't want to integrate over that. And I love integration, right? So let's see. Okay, how can we do this? Well, we can let y go from a function to a function and let x go from a constant to a constant, or vice versa. It doesn't look like it's going to be simpler one way or the other. So I would take this equation. Actually, let's take the version that we had before we divided by 4 and solve that for y squared. So we've got 4 equals 3x squared plus 2y squared. Subtract the 3x squared from both sides. Divide both sides by 2. And then you've got 2 minus 3 over 2x squared equals y squared. And you'll have a plus or a minus over here. So y goes from the negative square root of 2 minus 3 over 2x squared to the positive square root of 2 minus 3 over 2x squared. Meanwhile, x goes from this constant to that constant. And that's enough. So the constant bounds go on the outside. X goes from that lower bound to this upper bound. The variable bounds for y that depend on x, they go next. So that's describing the rest of the region R. Y goes from this negative square root to this positive square root. And meanwhile, z goes from the elliptic paraboloid to the cylinder, given by that. And that represents our volume. Now when I integrate with respect to z, well, actually I think we might be able to do this really quickly. Let's find the volume of that solid. I'm integrating 1 with respect to z, so I just get z. And we evaluate from the lower bound to the upper bound. Okay, so upper bound is 4 minus y squared, lower bound is 3x squared plus y squared. Sorry, it's so messy. Distribute the negative. So we'll have 4 minus y squared minus 3x squared minus another y squared, so that's a minus 2y squared. Integrate all of that with respect to y. So you have 4y minus 2/3 y cubed minus 3x squared times y. Oh, this is going to be ugly. We integrate from the negative square root to the positive square root. Yeah. We could do it, but if we replace y with that, and we subtract, we're going to end up with something that requires a trigonometric substitution. Then we're going to have this square root cubed here, also requiring a trigonometric substitution. And then this other one, this times the x squared, and the 3 doesn't really matter much. Like that we could evaluate probably with integration by parts, or yeah, integration by parts would probably be our best option, but it's going to take a while, longer than I have left in this video. So I guess we'll just stop here. But that's the idea, guys. If somebody asks you to set up a triple integral representing the volume of a solid region, you have to identify the top function and bottom function for z. So z is going to go from the bottom to the top, smallest to largest. And then you find the projection onto the xy plane. And generally the way you do that is you set the z values equal to each other for the bottom surface and top surface. And then you're going to end up with some curve in the xy plane, and you'll have to sketch that curve. Now sometimes it's an open curve. Sometimes you're going to get y equals x squared, and it doesn't have a boundary like this. In that case, they had to give you some other information to give you the rest of the boundary of R. The region R that you're integrating over has to be bounded in some way. So you find R, you find the projection of Q onto the xy plane, you describe it with the appropriate bounds. So y goes from a function to a function, and x goes from a constant to a constant, or vice versa. And then you do this. The innermost bounds, the bounds for this variable, can depend on these two. The bounds for this variable can depend on this one, and the bounds for the last variable have to be constants in order for you to get a volume out. So that is our introduction to triple integrals that represent volume, and we'll do more examples in another video.